Thanks everyone for coming. I will be talking about structured dynamic models of meaning for understanding how language changed over long periods of time, and also how meaning develops over long narratives like fictional books. So the talk will consist of two parts, which are entirely separate. You're very welcome to ask questions at any time, and I will probably also have a quick break between the two parts to have you ask questions. But yeah, let's get started. So in general, in my research, I try to be interdisciplinary. I try to use techniques from natural language processing and machine learning and apply them to understand phenomena in the world. I've worked on cognitive science problems like category acquisition, category learning in humans and infants. And I've also looked at problems in the social sciences as those that I will talk about here now. And I'm interested in using and developing these models for understanding those phenomena, so to use latent variable models and also some deep learning, but to make sure that the outputs are interpretable and understandable so that we are able to infer something backwards about what's happening in the real world. So to be a bit more concrete, I will talk about two projects that fall into this general paradigm. In the first part of the talk, I will talk about how language changes over centuries, how word meaning changes. And in the second part of the talk, I will talk about how we can learn structured multi-view representations of long stories, of fictional narratives. Okay, let's start with the dynamic meaning change. Natural language is inherently ambiguous. Words have different meanings, can have different meanings, sentences can have different meanings. And one famous example is the word mouse, which might refer to the animal, it might refer to a shy person, or it might refer to a computing device. And typically, the context in which these words are uttered disambiguates the meaning of a particular word or sentence. So if you're in the office with your colleagues and someone says, "Pass me the mouse," you can probably infer that that person is referring to the computational device. This is one example of how meaning can be dynamic, but there's another dimension, a temporal dimension. Language is also a dynamic system developing over time. It is constantly shaped by its users, by its speakers, and by the needs that those speakers need to communicate, and also by changing conventions. To give you an example of how meaning can change, the word nice about 700 years ago meant stupid. 300 years later, it meant something like lazy, and then the meaning became gradually more positive. And nowadays, when we refer to something as nice, we usually mean that it is pleasant or good. Another example is again the word mouse, which up to about 20, 30 years ago had one very prevalent meaning or sense, which is the animal sense. But over the last 30, 40 years, it acquired a new sense, which is the technical device sense. And that became more and more prevalent over time, just because of how our environment changes. It changes how we use language. And in this work, we try to capture this exact development. And language changes smoothly and slowly, especially in written language, because the changes need to propagate through societies and through communities, and speakers must agree on how they refer to certain things. The general framework of this work is distributional semantics. So a very prevalent paradigm in natural language processing is the distributional hypothesis, which has been proposed by different people a long time ago and has been proven many times. And it says that a word or a word's meaning can be defined by the contexts in which this meaning occurs. And here's an example. So we can look at a certain target word, let's say mouse, and we can look at large collections of texts and look at in which context this word occurs. And the context allows us then to disambiguate the actual meaning in this particular instance of the word mouse. And based on how often a particular sense occurs, we can characterize different senses and also characterize their prevalence. We can see how often and how important a particular sense is. And in this work, we add another dimension to this paradigm. We again look at words and contexts, but we take those contexts with their year or their time of occurrence. And this allows us to not only identify senses and their prevalence, but also to see how different senses change over time and how they change in importance over time. So in this work, we want to understand, model, and ultimately possibly be able to predict meaning change at scale from large data sets of corpora. And this is an important problem because it might aid historical or sociolinguistic research. These researchers are confronted with larger and larger data sets, and it might be useful to be able to point them automatically towards interesting places in those data sets where interesting change might be going on. Such a model might also be useful for improving historical text mining or information retrieval. If we can rule out certain senses of words at particular times, it might be able to update and construct ontologies. And a particular motivation for this work was to learn time-specific meaning representations of words which are interpretable but also task agnostic, so useful across tasks. And in the paper, we have a whole range of different evaluations where we show that indeed our representations are applicable across many, many different tasks. And I will talk about 3 of these later in the talk. So I'll say a few words about our data set. In order to do this research, we need a big corpus which stretches centuries of time in order to induce time-specific meaning representations for this period. And our data set consists of 3 parts. The first one is a corpus taken from a Semival task, which stretches 300 years from 1700 to 2010. And it consists of news text snippets from these times. The second corpus is the Cohab corpus, which is a much, much bigger corpus of 400 million words from of different genres, but it only stretches the years 1800 until 2000. So in order to also get a bit more coverage on this early period, we have a third corpus, which consists of texts from online open archives like Project Gutenberg, and it's mainly historical fiction texts. One obvious question might be, why did we not use Google Books, which is a huge, huge corpus of n-grams, so very local contexts, only 5 subsequent words. It's a huge collection. It stretches this entire period, but because the contexts are so short, it's difficult to actually learn sense-level information for words in a good way. So all the corpora we use provide us with full text, so we can look at longer contexts. From this big corpus, we extract word mentions in local contexts of 5 words to the left and 5 words to the right, and tag them all with their year of origin. And we also apply some pre-processing. We delete stop words. We do some lemmatization and tokenization. OK, then let's talk about the actual model, which we call SCAN, a dynamic model of sense change. The input to our model is exactly a corpus, like I just described how we obtain it, words in context, annotated with their year of origin. And then our model takes a couple of parameters. It is parameterized to the number of senses that we assume this word has throughout time. So we fix the number of senses. We might assume a priori that the word mouse has 5 senses. And then our model learns word meaning representations for contiguous temporal intervals. And we need to define what we mean by a temporal interval. We need to define the time where we start tracking meaning, where we end tracking meaning, and then chop this time up, for example, into decades, into centuries, into years, and then we learn one individual representation for each of those intervals. That's another parameter that we put into the model. Our model is Bayesian. It is knowledge lean in the sense that we don't need parsers or any heavy linguistic preprocessing. And on a very high level, it works as follows. We assume one target word whose meaning we want to track, for example, the word mouse. And then for each temporal interval t, we induce a distribution over the different senses of this target word. And for each of those senses, we induce a distribution over words that characterize this sense. And senses will be referred to as k throughout the talk, and words to w. And this is all conditioned on the particular target time t. And we don't do this only for one time, but for many, many times, all the intervals in our data set. And additionally, we also assume, because meaning changes smoothly and gradually, that these parameters between consecutive time steps depend on each other. So the meaning, the importance of different senses will not just radically change from one time to the next, but we assume that it's smooth and gradual. So we introduce these dependencies. To be a little bit more technical about the whole model, I'll describe it in terms of its generative story. Like with the generative story, you can define how you map your observations in the real world to latent variables and which relations you assume between those latent variables such that the observable data actually comes out of your model. So the generative story of the scan model goes as follows. We start by generating a parameter which controls the sense flexibility of our particular target word. So we model how much we learn, to what extent every particular target word changes over time. Given this parameter, we generate time-specific parameters. So for each time, t-1, t+1, we generate a distribution over senses for the particular word. And for each sense and each time, we generate a distribution over words for that sense. And all of these are connected. That's where the smoothness of change comes in. And I'll talk a little bit more about how these connections actually work on the next slide, but ignore them for now. And then given these time-specific parameters, we can generate data for each particular time interval. And we do this by drawing a sense for every data point from the time-specific sense distribution, and then drawing a bunch of sense-characterizing context words from the particular sense word distribution. So how exactly do we incorporate the temporal smoothness? We use a first-order random walk. And in particular, we draw the local changes of the word meaning distribution, for example, from a normal distribution. And the mean for every time steps normal distribution depends on the neighboring current means. And the variance depends on the meaning flexibility parameter that I talked about on the previous slide. So the extent of meaning between consecutive time points is also a parameter of this model. And then we derive a Gibbs sampler for approximate inference, but I won't go into any detail about that in this talk. We are not the first ones who look at how meaning changed over time, and we're also not the first ones who try to model it automatically. Other work has adopted the distributional semantics framework to characterize these properties. They have looked at corpora from two separate time frames and have characterized the meaning of individual words. But they do not have a smoothness of change assumption in their model, and they also don't look at the sense level, but only at the global word level of meaning. But their model is also knowledge lean, so no parsers needed, pure co-occurrence statistics based. Another related model looks at meaning change as a graph clustering problem. They characterize the word's meaning by inducing a graph and then cluster this graph of context words into different senses or into different local densely connected graphs. So like our work, they also look at meaning at the sense level, but they induce entirely independent graphs for every temporal time step. So there's no smoothness assumption, and also they depend on dependency parsers. So it's quite knowledge heavy and possibly not as generalizable as our work, and also more difficult to apply to older texts because the grammar is different and current up-to-date dependency parsers are trained on text from our times. Okay. In our evaluation, we will compare against some of this work. Actually, against all of this work in the paper, but I will not talk about all the evaluations in this talk. There are two problems with evaluation in this general sort area of work. There are no gold standard test sets and no benchmark corpora on which everyone compares their models. And also, a lot of evaluation has been small scale, where model developers pick some test examples and look whether their output confirms their intuitions, but it wasn't really objective on large scale. So to tackle the first problem, we constructed this big corpus consisting of 3 subcorpora that I already talked about, consisting of many hundreds of millions of words and spanning 300 years. And to tackle the second problem, we evaluate our model on a whole range of tasks and compare against the whole range of models. And also we evaluate an extrinsic task of temporal text classification, which I will talk about in a minute. But first I will show you some qualitative output. Here you can see what our model actually learns. So the target word for this particular output was the word battery. You want to know how the word battery changes in meaning over time. And here I show you a time scale ranging from 1700 to 2000. And each of these stacked bar plots covers a temporal interval of 20 years. And the segments in the bar plot refer to different senses, and the prevalence or importance of each sense is indicated by the height of this segment. And then I illustrate each of those senses as their highly associated words here at the bottom. And the grayed out bits are also senses, but for easier interpretability, I left them out of this plot. So we can see that for the word battery, a military sense emerges with associated words like gun and enemy, artillery. And this sort of military sense, represented by the green and yellow bits, was very prevalent in earlier times, but decreases in prevalence towards our time. And the pink and violet senses refer to the power or electricity meaning of the word battery. So here we have associated words like light and power and current and charge. And this sense becomes more and more prevalent and more important towards nowadays, which confirms our intuition quite nicely. Here's another example, same representation, but this time for the target word power. We learn a kind of mental, spiritual power sense, represented by the green and violet parts. We learn political power sense with important connotations like government, political, nation, war. And the spiritual power sense decreases over time slightly. The political power sense stays fairly constant, maybe becomes a little bit more important. And the third sense, again, refers to a kind of electrical sense, electricity, with words like company and electric plant. And this significantly increases in importance towards nowadays, which again confirms our intuitions. And we can not only look at how different senses change in prevalence, but we can also zoom into any of these senses and look at how connotations with that particular sense change over time. So I will now zoom into the electrical sense of the word power. And here you see words which are highly associated with that particular sense. The higher, the more highly associated, and time again goes from left to right. And we can see that with the electrical sense of the word power around the 1800s, 1800s, terms like water and steam were highly associated, but their level of association decreases over time. Whereas towards nowadays, terms like the word plant and nuclear become more and more important. So that again captures our intuition about what power meant to people over time and how that changed. This is all nice and good, but it would be nice to also quantify a bit how well our model does. So one way we attempted to do that was replicating a study or evaluating our model in a way that was proposed before in the literature by Goulordova et al. And they collected a gold standard data set by asking people how much they think individual words have changed between the 1960s and the 1990s. So how much do you think the word network has changed in meaning between those times? How much do you think the word basketball has changed in meaning between those times? And ratings were given on a 4-point scale from no change to significant change. And then they trained a distributional semantics model, basically counting co-occurrences between these target words and their contexts, and estimated the difference by cosine distance between the vectors that they obtained. And we applied our model to the same task, trained models on the 2 time slices, and then computed the correlation, the rank correlation of how much the models think a word has changed versus the ranks of how much humans think a word has changed. And we compare those using Spearman's rho. And here are the results. I show in violet our model, the scan model. In green, that's our scan model, but we cut the temporal dependencies. So we throw away the smoothness assumption and assume that the individual time meaning representations are independent of each other. And in yellow, I show the original work by Goulordova et al. And we can see, A, that cutting the dependence assumptions is not a good idea. Performance drops a lot for our model. We also see that performance seems to be fairly equal between our model and the Goulordova model, but I should say that the Goulordova model was trained on Google Books, so it's a different underlying corpus, so the numbers are not directly comparable. The Google Books corpus is much, much larger. this evaluation does not care about senses, you should note. So this is just about overall meaning change. So our model actually captures more than their model and was trained for this particular task on less data. So I think overall we can see that both models perform similarly, but it doesn't capture the full potential of our model. Okay, and then the final evaluation I'd like to talk about, here we applied our model to a Semival task from a couple of years ago, which involves presenting models with a news text snippet and asking the models to predict the time from which this news text snippet originates. So this is kind of an extrinsic evaluation of our word meaning representations. Here's an example. President de Gaulle favors an independent European nuclear striking force, and so on and so on. And the true time of origin is 1962. And models might figure this out because they are named entities which are highly associated with this particular time, or other grammatical constructions. You can use whatever information you like. The prediction task comes in 3 levels of difficulty. Either models have to predict within a 2-year interval where this news snippet comes from, a 6-year interval, or a 12-year interval. So it goes from easy prediction, hard prediction, to easier prediction because the target intervals become bigger. We apply our scan model to this task. We train scan models for 880 nouns and verbs, which we took from the development dataset of this shared task. We learn for each of these nouns and verbs a meaning presentation for each 5-year interval between 1700 and 2010. And we assume a set of 8 senses for each of these words. And then we look at test data snippets, and based on the representations that our model has learned for words in these test data snippets, we predict the time which has been assigned highest probability by our model. And here are the results. So we have a random baseline in orange. We have our full model again in violet. The crippled model where we cut the temporal dependencies like in the previous evaluation. And then IXA and AMBRA are the systems that originally participated in the shared task. And AMBRA uses a learning to rank mechanism. And IXA uses a whole lot, named entities from Wikipedia, WordNet information, also co-occurrence information from Google Books, and so on. And we can see that all models clearly outperform the random baseline, which is good. We can again see that cutting the temporal dependencies in our model hurts, so performance decreases quite a lot. And we can also see that both our models actually outperform the original models, which participated in the actual task, which is nice. One obvious question to ask might be whether we just used more training data, because we used our whole 500 million word corpus approximately. But I should say that these 2 models also used Google Books to approximate their word probabilities at particular times and so on. So they used extra data, not just this fairly small set of news text snippets provided as training data by the shared task. So I don't think this is purely a data size effect. And overall, we can see that the word representations we induced seem to be applicable to extrinsic tasks. Okay, to conclude this part, I presented a dynamic Bayesian knowledge lean model that learns how word meaning changes over time on the sense level. So we explicitly track different senses individually over time. We can arbitrarily track senses over wider or narrower temporal intervals for any size of a time span. And we explicitly model the smoothness of temporal meaning change. And this work opens up new avenues. We can apply it to different actual tasks, like historical text mining, building and updating ontologies. Or another thing we might be interested in the future is applying it to more short-term notions of change, like opinion change on Twitter. But that's future work. And that concludes the first part of this talk. If you want, you can ask questions now, or we can take them all to the end.
Any burning question? I have a couple. Maybe it helps break up the talk, right? One is, so your corpus is mainly news. Sorry. Your corpus is mainly news text, right? But you also have books and fiction.
It's actually mostly books and fiction from the Koha corpus, where actually the Koha corpus also has a lot of nonfiction, so it tries to be balanced across genres. And the fraction of news data in our overall data set is quite small because the Koha is so overwhelmingly big.
Because my question was about genre balance and whether what you're observing is also a reflection of the characteristics of the corpus and the type of topics that are talked about.
Definitely. Topics for sure. As you see, just with the word mouse, there was no computer topic back in the day, so that's definitely reflected. I hope that we control for genre, or I'm confident that we control for genre to some extent because the Koha, this huge corpus, aims to be genre balanced, sort of. But I think that's also some interference based on that, realistically.
To some extent, it's unavoidable whenever you compile it. And the other question was about the number of senses that you set at the beginning.
Mm-hmm.
How would you change a model to make that variable instead of constant? So instead of making k equals 8.
So there's a whole different paradigm of non-parametric Bayesian modeling where you don't set your parameters, but induce or let the model infer its own complexity in a data-driven way. If the data becomes more complex, the model becomes more complex and comes up with more topics, senses, clusters, whatever. So that would be a very principled way to make it work, but these non-parametric Bayesian models need a lot of data usually, and I'm not so confident that they would work great with the portions of the earlier times in our data set, which have way less data than we have for the 1990s and so on. And also, in our model, we set our parameters in a way so that the model becomes sparse. So we encourage sparsity in the model. The model does not always have to use all those 8 senses. It's kind of an upper bound. For some time slices, it can use less than those 8 senses. And you saw that when I showed you the stacked bar plots, some of the senses were very unimportant at certain times, and they changed. So our model allows us to do that. There is an upper bound of fixed 8 or whatever senses, but the model doesn't have to use all of them all the time.
Thank you.
It might be a bit of a stupid question, but how do you account for spelling reforms?
How do we?
How do you account for spelling reforms?
Oh.
Because, spelling changes over time.
Yeah.
So.
I guess, if spelling changes, these 2 words would be considered as separate tokens in our data set. So we do not normalize over that. There's no way our data accounts for that. Yeah. It would be nice if we could observe that these 2 words actually co-occur in the same senses over and over, but we did not really look at that. But yeah, it's an interesting question. I haven't thought about it at all. Okay. Then on to the next part, which is a total cut, total new problem, total new framework. Now we move on to how we can induce structured multi-view representations of long texts, and in particular stories in fiction novels. Why is this an important problem? So here I show you a graph of the number of US fiction titles published between 1940 and 2010. And we can see a dramatic increase from the mid-1990s when the internet came along and self-publishing became a lot easier. So there's no way to keep track of all the new titles being published nowadays. So when we go to a bookstore, we might find ourselves in a situation like this, where there's a huge selection and we just can't simply search through and find the best book we want to read on our own. So what we really need is some helpful bookshop assistant who we can ask all our questions and who we hope has a better overview than we have. And we might have very specific and very different demands. So we might want a book about space pirates, or we might want a book about secret baby romances. So we might want a particular type of character in a book we want to read next. We might want a particular sequence of relations between characters. We might want a particular mood or a particular topic. It can be all kinds of structured preferences. And the fact that these structured, diverse preferences exist is further supported by online book recommendation or book selling platforms. So Goodreads, for example, tags all the books in their database. Users tag them themselves. And the tags are very diverse. We have character type tags like vampire books. We have general topic tags like arts or sciences or Christianity. And we have genre tags like adventure, but also very specific genre tags like paranormal romance or contemporary romance. And you can maybe see that even under these very specific tags, there are still more than 500 books listed. So you can't search arbitrarily deep and arbitrarily specifically. Another example is Amazon, where they themselves structure the tags into different types. So for mystery books, you can filter further by specific character types like police officers or private investigators. Or you can specifically look for funny fantasy books or military fiction books. But again, even in all of these very specific tags, there are hundreds of books still listed. And these Amazon tags are actually provided by the publishers, so they are sort of expert provided. And it's not scalable to arbitrary scale. So in this work, we would like to do a develop a data-driven method of arbitrarily refining these already quite specific tags and recommending books based on these interpretable similarities that books have. So we take the raw content of a book and we induce multi-view representations of this book. And in this work in particular, we learn the properties of characters that are featured in a book. And we learn the relations between pairs of characters that are featured in the book. And for each of these, we also learn how they develop over time, over the plot of the book. We explicitly encourage these two views to be distinct from each other and to each encode relevant information. And we then use these structured multi-view representations of our books to cluster books together in model space. And we hope that these local clusters actually reflect meaningful correspondences or meaningful similarities between books. And this is all fine and good, but as you can probably imagine, it's difficult to evaluate. So how do we know that our model-induced clusters are actually meaningful? And we propose a new evaluation framework where we use the book tags from the Amazon catalog, which, as I said, are publisher created. So we assume that they are very accurate and can be taken as a gold standard. And then we look at the microclusters produced by our model and verify that the books in those microclusters actually share tags from the Amazon catalog. And this is an objective, scalable way of evaluating our model output. It allows us to induce clusters over tens of thousands of books, and we still have an efficient way of evaluating that without having to look manually into the model space. There's quite a bit of prior work on automatically understanding what happens in a book or in a plot. People have looked at typical event chains, typical characters in books. They have looked at the network, the social network of characters between characters in a book. And quite recently, there's been a model proposed which looks at relations between characters and their development over time. And in this work, we take this model and extend it to induce multi-view representations. And we introduce a new loss function for this model. And yeah, this model is the RMN. I will keep talking about it and compare it to our model, and we will also evaluate later against this underlying model. In terms of previous evaluation, people have manually analyzed their output. People have also shown their model output to experts from the literary sciences and asked those experts whether they find the model output meaningful. They've created small gold standards. But they haven't really, these are all extrinsic measures which don't really tell us whether their model output is actually applicable to extrinsic tasks. One exception is the work by Elsner, who tried and evaluated whether his model can distinguish between actual stories and artificially scrambled stories, where he just shuffled around the chapters of a novel, which is kind of an extrinsic task, but it is again artificial, and it's not clear how that generalizes to real-world tasks. So in this work, we propose the scalable evaluation framework where we use the Amazon book tags to evaluate model output space at scale. Okay, next I will introduce our model MVPlot, a multi-view plot representation model. We take as input a book, and for each character in this book, we learn a representation of the character properties and their development over time. And at the same time for this book, we look at important pairs of characters and look at in what relation these character pairs are in, and look at how these relations develop over time. And I will talk about character properties as view 1, and about the character relations over time as view 2. Both the properties and the relations eventually are word clusters. So this is all an unsupervised clustering model. It's a bit like a topic model, and you can think of these like topics in a topic model. And I will talk a little bit later about the objective, which explicitly enforces those two views to be distinct from each other and to be each coherent and relevant to the information that the view is supposed to capture. We have a view-specific input corpora. So in order to learn view 1, the property view, we have local text spans, which mention only one particular character of interest within local context, but no other character, assuming that these local contexts convey some information about the inherent properties of that character. And we look at 20-word text spans. And these text spans are chronologically ordered with respect to their occurrence in the novel. We have a separate input corpus for the relation view, where we look at similar local text spans which mention two characters whose relation we are interested in within local context, but no other character. And again, they are chronologically ordered. And we don't only look at one character and one relation pair, but at many, many individual characters and many, many character pairs from many books, and all the pairs and characters in those books. So we get two separate view-specific input corpora. We map all the words in our corpora to pre-trained word embeddings, and in order to get a span-level input for our model, we average the word embeddings for all the words in that span. The output of our model consists of 4 parts. So first, we learn a global set of property descriptors, or topics which refer to properties of individual characters in the book. We also learn a separate set of topics or descriptors for relations between character pairs. So for example, we might learn a property which captures the intellect of individual characters or the look of individual characters. And we might learn a relation which captures a relation like love or a relation like hate. And these are global and shared over all the books in our input corpus. But also for each individual character in each book, we learn a property trajectory. And for each individual character pair in each book, we learn a relationship trajectory. And these are sequences of probability distributions over these topics, over their respective sets of topics. More formally, our model falls into the framework of the autoencoder, which is an unsupervised deep model. And it works as follows. You give an input to the autoencoder, which in our case is a text span mapped to word embedding space. And the autoencoder learns to map this input to a lower dimensional latent representation, which captures the gist, just the most important aspects of this input. And it learns these representations in a way so that it's then able to accurately reconstruct the original input. So what is the gist that we want to learn in our model? We want to learn the property descriptors and the relation descriptors. So we learn to map input text spans into probability distributions over these descriptors. And we learn two separate dictionaries, or two separate sets of descriptors, a dictionary over property descriptors and a dictionary over relation descriptors. And then we reconstruct the original input as a linear combination of these descriptors. And I should say that this general setup is the exact same setup as the one of the model that we are extending. The only extra bit that we do is that we learn these two descriptors, so we have a multi-view setup. The original model only learned relations between characters, but nothing about individual properties. And then as a final bit of information, this model assumes that a property of a character at any time depends on the properties of a character at the previous time. So properties of characters don't just arbitrarily change from one time to the next. So there's a little recurrence in there where the previous properties influence the current times properties, the previous relations influence the current times relations. Okay, here's some more formal overview over the model. We have as input an embedded text span mentioning either an individual character or a pair of characters. We learn to map this to a hidden representation, and then we propagate this representation through the model. We learn to map the hidden representation to a feature vector, which are weights over the terms in our dictionary. We have a property dictionary and a relation dictionary. And then we reconstruct the original input as a linear combination governed by the weights that we map to of the terms in the dictionary. And we reconstruct our original input. And note that the original input is in word embedding space. And because we reconstruct a word embedding space representation, our dictionary also lives in word embedding space. And we can visualize all the terms in the dictionary as the words most closely related to these terms in space.
Maybe not everyone knows about word embeddings in this room, so if you can just say a couple of words about that.
Okay. These are just vectors of numbers in some space which are induced in a way that similar words or words which occur in similar contexts are closely clustered together in this latent space. So you assign each word a vector of numbers, and words that are similar in some way should end up in a closed location. And depending on how you train these models, you can use any context, just the raw word context. You can use context in a parse tree or whatever means you are interested in. And there are pre-trained spaces available, trained on very, very big corpora. And people use these pre-trained vector spaces typically in their models. So we assume that the space is already there. Yeah. So again, the original RMN model that we are extending looks very similar to our model, but it would only consist of one part, only the relation part. And we extend this original model by adding another part and do the multi-view learning. And by just looking at this, it seems like this is entirely symmetric, right? It is not clear at all how we end up learning different representations in these two parts. And we learn these two different representations through the multi-view loss function, which triggers distinct parameter weights in each of these parts. So how does the multi-view loss function look like? Intuitively, within each of our views, the property and the relation view, we want to train an autoencoder in a way that it is very good at reconstructing the original inputs from the latent representation. But across views, we want parameters that are different, so that encode distinct aspects. So within each view, we use the standard contrastive estimation with negative sampling framework. And for each training iteration, sorry about that. We have one true input to the model, which we pass through our model, and we obtain a reconstruction of it. And we want this reconstruction to be very similar to the original input. But at the same time, we have some random inputs, which we just sample from our corpus. And we then compare the reconstruction of the true input also to the random inputs. And since they don't have anything to do with each other, we want them to be far apart in model space. So we tweak our parameters towards this objective to be very well able to reconstruct the true input to maximize the similarity, but to do very badly at reconstructing random inputs to minimize the similarity, to pull them apart. And we do this individually for each view. We have the exact same objective within the other view as well. But this is still entirely separate. So In the second part of our loss function, we introduce dependencies between the two parts and make sure that the parameters are actually distinct. And we do this again by using this contrastive estimation framework. We have one true input. One input, let's say it's from view 1. We pass it through both portions of the model, and we look at the reconstructions. And now we want the V1 part of our model to be very well able to reconstruct this V1 input, so to maximize the similarity between the reconstruction and the true input. But at the same time, we want the relation part to do very poorly at reconstructing property inputs. So we want to maximize the similarity of the relation view output from the, with the property view input. This is how we pull apart representations in model space. And it works the same way the other way around. Oops, sorry about that. It's entirely symmetric. Okay, so this concludes the model description. Regarding evaluation, we evaluate our model on 2 corpora. We have a very large corpus from the Amazon Kindle digital book corpus comprising 10,000 books. But this is not publicly available, unfortunately. So we also evaluate our model on a corpus derived from the Project Gutenberg, which is an open source library of fiction books available to everybody. We pre-process all our books using the Books NLP pipeline, which allows us to do named entity disambiguation, some part of speech tagging, and so on. And this is particularly developed for large texts. And we do some filtering. We only keep sequences of character mentions and sequences of character pair mentions, which are neither too short nor too long, because the too short ones are probably not important characters in the book, and the too long ones are probably due to pre-processing errors. So first, let's take a look of the property and relation descriptors that our model can actually learn. Here's some example output from the Project Gutenberg corpus, and we represent each of the descriptors as the 10 closest words in the word embedding glove space. And here are some property descriptors that we learn for individual characters. So we learn a kind of happiness emotion cluster. We learn a being comfortable or cozy cluster and a title cluster. And all of these refer to aspects of individual characters, right? Rather than things that happen between characters. So for that part, we learn a separate set of relation descriptors. And here are again 2 examples. We learn a love relation and also a professional relationship relation, like being an associate, being a president. These are all relational attributes between characters. So intuitively, it seems like our model does something reasonable and learns good and distinct descriptors. But we tried to quantify this also. And we went to Amazon Mechanical Turk and did a crowdsourced-based evaluation of how meaningful the relation descriptors between characters are. We asked Turkers whether they actually described relations between characters. And we compare the output from our own model against the original RMN model, which, as I said, only learns relation descriptors and not the multi-view representations that we learn. So we show crowd workers a relation, like induced by either our model or the RMN model, and we ask them, do the words describe a relation, event, or interaction between people, yes or no? And here are the results. So these are results for the original RMN model and our own model trained on Project Gutenberg data. And here we show which percentage of annotators rated which percent of descriptors as relevant. So very many, a large percentage of annotators found only very few descriptors relevant, but like 50% of all the annotators found about 50% of all the descriptors relevant. So this gives you a general idea of the overall quality, but what you should actually see in this graph is that the 2 lines look very similar. This is on the Gutenberg corpus, and this is on the Amazon corpus. Again, the 2 lines look very similar. And what we can deduce from this is that the relation descriptors emerging from our model are similarly intuitive to Mechanical Turkers as the relation descriptors emerging from the original RMN model. which we take as positive because we have the more complex multi-view objective, but we don't compromise in interpretability despite this more complex objective. Okay, and then in the final part, I will talk about this large-scale evaluation that I've been advertising before, where we use the Amazon book tags. We want to get a notion of if we cluster books in model space by the representations that we've learned for them, how good are these local clusters actually? And do books which our model finds similar actually share book tags, semantic book tags from the Amazon catalog? And here are some examples for those book tags from the Amazon catalog. So we have character type tags that we use for thrillers, for romance, for sci-fi. So there are different types of characters that appear in those genres. Here are some other examples where we look at different moods and themes that appear in genres. And these are just taken from the Amazon catalog. We use 50 such tags from popular genres and those which occur frequently in the catalog, so which are used a lot by the publishers to tag books. And we did not tune this tag set. We selected it very early in the project, and by the time we came to evaluation, we just used this very generic set. So the remaining question is, how do we actually cluster books? How do we compute a similarity based on the structured representations that our model induces? So recall that for each character in each book, we have a property representation, and for each character pair in each book, we have a relation representation through an average trajectory each over the property descriptors and the relation descriptors. And now we can cluster books based on these different views and ask which books are similar with respect to the property descriptors assigned to the individual characters, which books are similar with respect to the relation descriptors between character pairs in these books, and which books are just overall similar with respect to all the information that we have in our structured representations. And to do this, we take two books, book 1 and book 2. And in order to compute the similarity of two books with respect to their character properties, we look at each character in book 1 and find the character in book 2 which has the most similar representation to this character in book 1. And then we sum up all these minimal distances across all the individual characters in the two books. In order to compute similarity between two books based on their character pair relation, we look at all the character pairs in book 1, and then find the character pair in book 2, which has the most similar representation to the character pair in book 1, and do that for all the character pairs in book 1, and sum up all the minimal distances. And if we want to compute book similarity based on both these views, we do the two things individually and then just take the average. We do this whole experiment in a k-nearest neighbor framework. We select 500 reference books whose nearest neighbors we look at, whose 10 nearest neighbors in model space we look at, and then we look for each of those 10 nearest neighbors whether they share any tag from the Amazon catalog with the reference book. And we report our results as precision at rank 10. So how many out of those 10 books, 10 nearest neighbors actually share a tag with the reference. And here are the results. So we compare 3 systems. This is our own system. This is the RMN again, which only learns relation descriptors, but no multi-view information. So we only have one view here. And then we have a simple cosine baseline, which simply takes our whole corpus of books and computes similarity based on pure cosine distance, but does not explicitly learn anything about property descriptors or relation descriptors. We show the performance based on the property similarity in green, based on only relation-based similarity in orange, and overall similarity in violet. And we can see at least 2 things. So first, our model outperforms all the other models, which is nice. So it seems like the properties and relations that our model learns are more useful for semantically driven book clustering in model space, and more useful for replicating the semantic information that's there in the Amazon tags. And the other nice thing that we see is when we use both views, we do better than using any view individually. So this confirms that these two views indeed capture complementary information. Using them both gives us a boost, which is nice. OK, and here's some qualitative output. As I said, we have these 500 reference books. I show you 4 of them here. And then from left to right over here, I show you the nearest neighbors that our model clustered with those reference books. And we can see that Tarzan books are clustered close to a Tarzan reference book. Down here, we have a Jane Austen romantic 17th century book cluster. Here we have Tolstoy and other Russian writers. So we can see that these clusters are admittedly dominated by authorship. So books from the same author are clustered together, but not exclusively so. So up here, for example, we have Charles Dickens clustered together with Thomas Hardy, who are both famous for having this autobiography type of novels. They're both from the same era and have similar topics. So these nearest neighbors capture things over and above style and authorship, for sure. OK, to conclude this part, I presented MVPlot, a deep model of inducing multi-view book representations. In this work, we learned about properties of individual characters and relations between character pairs. I showed that our model works on a large data set derived from the Amazon corpus, but we also evaluated on a smaller corpus from Project Gutenberg books and got good results for that as well. And I showed that the different views actually result into quantitatively better clusters, showing that they capture distinct information. I introduced a multi-view loss function, which triggers the two views to capture distinct information and relevant information. And we applied this here to learning two views, but I should emphasize that this framework is very general. So we could induce another view with exactly the same method. For example, we could have a third view in the model which captures the mood of the book. And our loss function or objective would work in the exact same way. And finally, I introduced a scalable and very flexible evaluation framework where we compare model output against tags from the Amazon book catalog. And yeah, it's scalable, it's principled. We could do specific evaluations, for example, where we only look at character property tags from the Amazon catalog and do more focused evaluation of our books as well. So there's a lot of scope in developing this further. And to summarize the talk, I showed you 2 examples of recent work that I've done, of work where I tried to be interdisciplinary, use natural language processing and machine learning techniques at scale to induce understandable, interpretable representations, both of how meaning changes over time and separately of how book plots are structured and can be represented in an understandable way. Yeah, thank you very much. More questions?
I was wondering about the evolution over time of your characters and relations. So how do you find time in a book? Is it just in a relative way, yeah, or do you, because it's not obvious, as in the case of years, how you would use that? Because in a book you wouldn't have that. So
you mean that the story is not necessarily told in a chronological order, right?
Yeah, no, I mean, so you said these features change over time, and that is defined as where in the book
page
they occur.
Page.
Is it based on the page number?
Yeah, so we have these individual input snippets for each individual character or character pair, and these are chronologically ordered with respect to their occurrence in the book. So for each of these text snippets, we learn a property representation. So looking at them one after the other, we get a trajectory.
Okay, so it could be that the change is very fast at the beginning and then it levels off, or it could be very gradual. You wouldn't know.
It could be. We could look into that. We haven't done that specific analysis, really. We were more interested in doing this overall analysis in terms of clustering. But yeah, I'm sure we get a lot of very specific phenomena as well. And it might also be just the other way around of having slow change in the beginning and drastic change in the end. I think it's very book specific. And then there's the whole other problem of many books not being told in chronological order, right?
Yes.
So if that's not the case, then our assumption is a bit questionable anyway.
What about the books? The characters of which change name?
Sorry?
Some books have characters that change name. Like the Count of Monte Cristo. How do you account for that? Or it's just...
We do automatic pre-processing. So we do named entity recognition and coreference resolution with an automatic system. So what we do capture is when it says something like, Harry Potter said he would like to meet blah, blah, blah. So we know that this he pronoun also refers to Harry Potter. So in that sense, we capture all the boy who survived that would refer to Harry Potter. We capture this kind of information, but
I mean, it's only
someone
very
changing
few
names, I
books,
don't
so
think.
it might be not very important.
Yeah, no. And this is really more big data driven. So we capture the overall gist, and we assume that overall there's a constant character which develops from the beginning to the end, and small fluctuation would hopefully
smooth out.
True.
Just a comment. I was thinking, literary scholars may be interested in. I think they would be very interested in this type of research. I mean, they would have a different view, more close reading and more detailed. But I'm not aware of this large-scale type of analysis being done in combination with literary scholars. So it sounds like potentially an interesting collaboration avenue. Okay. Are there any more questions? Well, then we'll thank our speaker again.